Okay, so at the bedrock of astronomy, there's a paradox, one that they don't really teach you when you first enter the field. When you become a student of astronomy, you learn about the stars and planets, you learn about solar system formation and dynamics, stellar evolution and demise. You even learn about the creation and destruction of the entire universe. But there's one thing that they don't teach you, a hidden crack within astronomy itself that only comes with a bit of reflection. Here's what I mean. So I recently completed my undergraduate degree. I studied astronomy and philosophy. You can see the degrees over there as props, but they got left out in the rain, so they're a little bit wrinkly. That's enough of my credentials though. What matters is that it was sort of late into my journey into astrophysical and planetary sciences that the astronomer's paradox, as I've termed it, was sort of revealed to me. It wasn't taught to me. In fact, it was really sort of revealed over time. Perhaps this was just the philosophy side of my studies breaking me, but most astronomers don't seem to be aware of this paradox. It only becomes clear if you take time to stop and look. In fact, the more you look out, the more you're forced to look in. This is the astronomer's paradox, the battle between inner and outer space. So what do I mean by this? Well, in order to talk about this, we're going to have to traverse over 3,000 years of human history and over 13 billion years of cosmic history. So to understand what I mean by this, we're going to have to travel through a lot of time and space. That's going to be quite the journey to figure out exactly what I mean by this, like, astronomer's paradox, right? We need to cross a lot of human history and a lot of cosmic history. But first, what is astronomy? What exactly is this study and what is its jurisdiction? Astronomy is the branch of science that deals with celestial objects, space, and the physical universe as a whole. This is not to be confused with astrology, which is some bullshit. It's sort of a faux religion that used to be sort of metaphysically intertwined with astronomy. Even though they have the same origins, they are not the same. Astronomy is a science. In fact, it's the oldest science. But what in fact is a science? What is this thing that we treasure so dearly? Science is the systematic study of the structure and behavior of the physical and natural world through observation, experimentation, and the testing of theories against the evidence obtained. Observation, experimentation, and testing of theories. These are the three pillars of science. We watch the world, come up with questions, and then come up with theories to answer those questions. Then, the crucial part of science is that we test those theories. We test the theories until they break, and once they break, we realize, oh shit, we have to come up with new theories. Now, astronomy is a unique science in the sense that, at least historically, it is largely observation-based. We aren't in labs conducting experiments in the way that physicists or chemists might. We are out looking up at the sky. Now, this has been true for thousands of years. The first historical instance of scientific observation dates back to astronomers in ancient Babylon around 3,600 years ago. They did some killer astronomy, and they did it around 1,000 years before the Buddha, 1,300 years before Aristotle, and 1,600 years before Jesus Christ. They were doing it a long time ago. But by around 500 BCE, with the ancient Greeks, they really started to get it together. We started to have enough of an understanding of mathematics and enough data from observing the sky that we could start to piece together our understanding of things, to the point where even a natural philosopher by the name of Thales, and by natural philosopher I mean just proto-scientist, Thales was able to predict an eclipse ahead of time, using enough of his understanding of the sky, a bit of mathematics, to piece it all together. Thales was clever, but he also thought that the entire universe was fundamentally made of water, so we had a long way to go with science. After Thales, things really started to come together even further. We have Pythagoras to thank a lot for our understanding of astronomy in ancient times. Pythagoras and his cult of math, music, and space-loving friends. But then, a couple of centuries later, unfortunately, this guy, the philosopher Plato, accidentally fucked up astronomy for about 2,000 years. Quite the blunder. He convinced everybody that the motions of the celestial sphere, the motions of the things in the sky, they had to fundamentally boil down to perfect circles. Now, this was because Plato was an idealist. He thought that the motion of the celestial bodies had to be perfect. This, as we will see, was not true. So what I'm really trying to say is that we have Plato to thank for the fact that we didn't get to Mars around 500 years ago. That's a joke, but not really. For you see, there was a problem with ancient astronomical observation. When you look up in the night sky, you see two things primarily if you're just using your eyeballs. You see stars and you see planets. The problem is that to the untrained eye, these two objects look exactly the same. However, they move very, very differently from night to night. Stars stay fixed in place relative to one another, whereas planets, well, they tend to move from night to night. That's the reason that we've been able to tell eon-spanning stories across generations of human history by just looking at the stars and drawing lines between them. We can't do that with planets because they wander from place to place. The term planet actually comes from the Greek word for wanderer, because planets to the ancient Greeks were wandering stars. They were the stars that refused to stay fixed in place relative to one another. So this motion of these wandering stars, these planets that move throughout the constellations across the weeks and months, is actually really difficult to account for in a scientific theory, especially when you're locked into Platonic dogma that says everything needs to be perfect circles. This was clarified further by a writer. Let me grab something. This book is called The Sleepwalkers by Arthur Koestler. It's a history of man's changing vision of the universe. Now, in this book, he says the task of mathematicians after Plato was now to design a system which would reduce the apparent irregularities of the motions of the planets to regular motions in perfectly regular circles. This task kept them busy for the next 2,000 years. Thanks a lot, Plato. Okay, but this didn't halt every type of science, thankfully. The earth sciences remained sort of untouched for now, because by around 200 BCE, Eratosthenes was actually able to predict the circumference of the earth insanely accurately using just shadows and a little bit of geometry. But flat earthers be damned. But we still thought that the Earth was at the center of the solar system. We thought that the Earth was at the center of the whole universe, in fact. This is a dogma that it would take quite some time to overcome. Humans are pretty self-centered, so it makes sense that we would want to put ourselves at the center of the universe. This is something called geocentrism. Geocentric means having or representing the Earth as the center, as in former astronomical systems. Now, only one person in ancient times was clever enough to put the sun at the center of our solar system rather than the Earth. This was Aristarchus. He was a Pythagorean astronomer, meaning that he was a part of that sort of cult of math bros that was the Pythagorean Brotherhood way back in the day. And he said that the sun was actually at the center of the solar system. But unfortunately, that sort of geocentric dogma was too strong at the time, so nobody listened for about 1,500 years. And that's not it. By around 200 AD, things got worse when Ptolemy, who was another sort of mathematician, astronomer, polymath, he gave clout to geocentrism by sprinkling in some mathematics. He figured out a way to sort of make it work using a bit of math that made people think even more confidently that geocentrism was true. Ptolemy did everything he could to keep that status quo of geocentrism, and it worked for a really, really long time. It wouldn't be until the 16th century when Copernicus published a heliocentric model that the world accepted, more or less, or at least would come to accept, right? Now, heliocentric means having or representing the sun as the center, as in accepted as astronomical models of the solar system. So the church in Europe was losing its power, and minds began to open. So Aristarchus can breathe easy now that we've realized his brilliance, even though Copernicus gets all the credit. Classic. So this is where we more or less enter the age of true astronomy. In the late 16th century, before the invention of the telescope, there was somebody named Tycho Brahe. Now, this dude was crazy for a lot of reasons. He was a nobleman, he was quite wealthy, or at least came from a wealthy background, and he had an observatory built for him. He spent all of his time there. He was an intensely dedicated observer. He was one of the most dedicated observers since ancient Babylon, and he collected an unmatched data set of the sky. He took his job so seriously that he once got in a duel with like swords with another nobleman over who was the better mathematician. He lost the bridge of his nose in the process and wore a like gold or brass or silver prosthetic for the rest of his life. Pretty metal stuff. I'd like to see current mathematicians taking it that far. Okay, that's dumb. Brahe spent decades in his observatory taking astronomical observations. So his data was really unmatched at the time, and there was one person who needed that data most. because at the current time, it was just data. There was no theory that was there to sort of synthesize all of that information. Tycho Brahe, being a arrogant scientist, wanted to take the credit for coming up with some sort of theory. But quite frankly, he wasn't able to do it. This is where Kepler enters the scene. Johannes Kepler was essentially the opposite of Tycho Brahe in pretty much every way. But he came in and he was able to use Tycho Brahe's data set in order to synthesize physics and astronomy and come up with some actual laws that governed the universe. In particular, he was responsible for 3 laws of planetary motion. Kepler was a genius, and quite frankly, he's underrated in the history of science, to be honest, because he was the one that first synthesized astronomy with physics and brought everything together into some coherent laws. These are Kepler's 3 laws of planetary motion. They are 1, the planets move in elliptical orbits with the sun at one focus. 2, planets sweep out equal area and equal time across their orbits. And 3, there is an exact relationship between the squares of the planet's period and the cubes of their average distance from the sun. That's a lot, but it's actually a lot simpler than it looks. These 3 laws were published in his 1906 magnum opus, which had an incredible title. Okay, let's see what this title was called. This title was called A New Astronomy Based on Causation, or a Physics of the Sky Derived from the Investigations of the Motions of the Star Mars, founded on observations of the noble Tycho Brahe. He knew how to write the title of a book, that's for sure. But put simply, these 3 laws say a lot and very little at the same time. Put simply, these 3 laws mean that planets move in ellipses, not circles, and that if they're closer to the sun, then they have to be moving faster, and their year must be shorter. This is the holy trinity of solar system dynamics. And it all seems pretty obvious to us now, but at the time this was revolutionary. This broke out of that sort of Platonic dogma of thinking that everything must be perfect circles, where planets move at the same speed all the time. So Kepler changed everything because he was the first one to remove astronomy from theology and sort of merge it with physics. This is when astronomy was completely divorced from that sort of metaphysics of astrology and was married to science, as Arthur Koestler puts it. So then, in the late 16th and early 17th centuries, Galileo Galilei became the first to point telescopes at the sky, and as a result, he was able to peer back farther than anyone ever had before. This was kind of like giving a kid a white monster, like it helped them see the Matrix, but they kind of just spazzed out and they could see things they could never see before. Anyways. What Galileo saw changed everything. He looked up at the sky and he saw craters and valleys and mountains on the moon. He saw a sun that had sunspots on it. And when he looked at the Milky Way galaxy, he didn't see a fuzzy band, he saw individual stars. That is to say, when Galileo pointed his telescope up at things in the sky, he revealed that the Platonic dogma of cosmic perfection might not be accurate. Perhaps the sun is covered in spots. Perhaps the moon is actually a worldly body just like our own. Perhaps the Milky Way is comprised of suns just like our own. To once again quote Koestler, the mountains and valleys of the moon confirmed the similarity between the heavenly and earthly matter, the homogeneous nature of the stuff from which the universe is built. The unsuspected number of invisible stars made an absurdity of the notion that they were created for man's pleasure, since he could only see them armed with a machine. Armed with a machine. That's a pretty cool quote. Now, more than anything, this means that a simple lens could show us things that we couldn't see before. It unlocked astronomy for us. Now, one of my favorite examples of this ever is the sort of dark spots on the moon. They're called mare or maria. Now, they're called maria because originally astronomers thought that they were seas. If you look up at the moon and you don't really know what you're looking at, a darker spot could sort of come off as looking like an ocean from a distance. Now, it turns out, now quite obviously, that those were not seas. In fact, they are more seas of basaltic lava, or ancient basaltic lava plains. We can sort of see this lineage going back, right? We call them maria because we thought that they were seas. We still call them maria to this day because that sort of heritage of astronomical confusion goes way back. Galileo pointing his telescope up at the sky was just the first of many steps forward that kind of changed everything. So outer space mirrors Earth in bizarre and interesting ways, right? We have these seas on the moon, these maria, but they're not seas of water, they're seas of basaltic lava, or what used to be basaltic lava. Galileo started to unlock this. He was the first to sort of get rid of that Platonic dogma and say, hey, outer space is actually like Earth, but not exactly. It's not this cosmic perfection that we had come to expect. Still, our astronomical tech was very much in its infancy. We had yet to unlock the power of mirrors. Mirrors changed everything. Up until this point, we had only used what's called refracting telescopes. This is what Galileo used, and it's very simple, which is why we used it in the beginning. However, it's optically limited. It has a lot of issues as far as things like chromatic aberration, which is where the wavelengths of light get separated and it results in sort of distortion, especially when you're looking further out at very faint things. Chromatic aberration is a result specifically of light being distorted when it comes through a wide aperture. You can sort of maybe see it here in this footage of these flowers in this camera, where you can sort of see the colors getting distorted around the edges of the objects. That is chromatic aberration, and it becomes even more extreme when you're looking at things that are faint and far away. So this is obviously a problem when in astronomy everything we're looking at is faint and far away except for the moon and the sun, essentially. Things like chromatic aberration became especially frustrating when looking at very, very faint and distant objects like nebulae, for example, TBD, to be discovered. One super obscure scientist with an affinity for apples had had enough. In 1668, Isaac Newton became the first to utilize mirrors in his telescope. He had had enough of the refractory telescopes with all their chromatic aberration and distortion, and he decided to create a reflecting telescope, the first of its kind. So suddenly mirrors became the symbol of modern astronomical discovery. We realized that we can create much larger, more powerful mirrors than we can create lenses. This unlocked things further for us. Now, mirrors were the first step, but in the last 50 years or so, we've realized one thing further. As far as our telescope building philosophy goes, we've realized that, well, the best way to look at things in space is from space. So we've combined the philosophy of using mirrors instead of lenses, as well as the philosophy of putting those mirrors up in space to avoid atmospheric disruption. Essentially, with all of this combined, we're trying to get as much light as possible with as little distortion and disturbance. So this, my friends, is why we left for space.
Liftoff of the Space Shuttle Discovery with the Hubble Space Telescope, our window on the universe.
Yes, badass space montage. So Hubble and the James Webb Space Telescope, those are the canonical instances of the combination of this philosophy. Let's put giant mirrors up in space and try to collect as much light from the universe as possible. Now, the James Webb Space Telescope specifically is the peak of this technology today. Galileo would have lost his mind. Now, this projects us into the age of postmodern astronomy, where our astronomical discovery is more method than myth. Astronomy is focused on the subjects that are beyond the Earth. And what we'll come to discover, and what astronomers through the history of science came to discover, was that that is, for all intents and purposes, everything. Everything else in the universe is outside of the Earth. Now, I know that sounds silly, but our sort of world here that we look at is a tiny, tiny fraction of what's in just our solar system alone, let alone the galaxy, let alone the trillions of galaxies that there are. And as we'll see, with telescopes, we began to really be able to contextualize who we are as a species and what our place is within the universe. As we've learned to peer back farther and farther into the universe, new struggles have arisen. Now, one of these main struggles that astronomers have had to come up with creative solutions to is distance. If I want to measure the distance to that tree over there, I can walk and see how long it takes me, or I could get out a tape measure and measure how far away it is. You can't do that if you're looking at planets or stars or galaxies. How can you tell how far away something is? This is where astronomers have had to get creative. It turns out that we can't use one solution to determine the distance to all objects. The method that we might use to measure the distance to Venus, for example, is drastically different than the method we would use to measure the distance to a galaxy far away from our own. Now, this is what astronomers have called the cosmic distance ladder. They've had to use different methods to determine distances of different objects. Now, what's clever and also kind of limiting about this system is that each step of the ladder calibrates the next one. So we'll see where that runs into some troubles later, but it's what has allowed us to measure the distances to the farthest galaxies in the known universe. But this is our investigation into the cosmic distance ladder. Spoiler alert, you can see it here, but I suggest that we actually walk and let's visualize what this looks like. Okay, so for close objects like the Moon and Venus, we use something called radar ranging. Essentially, we shoot a beam of radio waves, radio light, at an object and time how long it takes for that light to hit the object, bounce back, and then come back to Earth. Then, given that we know the speed of light, we can adjust and figure out how far away that body is. So this works really, really well for solid bodies that are close to us, like within our solar system, but it can't work for very distant objects that aren't reflective, like stars, for example. We can't shoot a laser beam at a star and time how long it takes for it to bounce back at us. For that, we need to use something called parallax. So beautiful. Whoa, that's a cool bird. Parallax is insanely clever. Essentially, astronomers have realized that as the Earth orbits around the Sun, it orbits in an approximate circle. It's actually an ellipse, as we learned earlier. But as it orbits, it changes its perspective on the surrounding stars. So essentially, the background stars shift slightly in comparison to where we look at a single star. I'll draw a bit of a diagram. But essentially, you can demonstrate it by holding out your thumb at an arm's distance and then closing one eye and switching between your eyes. You'll see that the background changes its position slightly relative to where your thumb is. That's what parallax is. We're just doing that on a galactic scale. Now, this works for only about 75,000 light years away, which sounds like a lot, but that's really limited to just our galaxy. We can't use this beyond our galaxy. So beyond our galaxy, we've had to get clever. This is where things get interesting. How do we figure out the distance to a galaxy outside of our own? It's too far to really do any of the measurements that we've used thus far. So we've had to get quite creative. What we end up using is something called a standard candle. This is something that has a set brightness where we know the brightness, and then we can figure out how far away it is based off of how dim it is in comparison to that intrinsic brightness. If we know that a light bulb, for example, has an intrinsic luminosity of 60 watts, if we then move it farther away from us, it'll get dimmer. And we can measure how much dimmer it gets to determine how much farther away it is. That's what we're doing with these standard candles. Now, the universe has blessed us with a few of these standard candles. One is the Cepheid variable, and the other is a type 1a supernova. Cepheid variables are a type of pulsating star, meaning that their brightness actually changes over time. It sort of pulsates back and forth between being brighter and being dimmer. The rate at which a Cepheid variable pulsates corresponds directly to its intrinsic luminosity, meaning that if we can look at a Cepheid variable and we can measure how quickly it's pulsating, we can know how bright it's supposed to be. Then we can, as I was explaining, compare that intrinsic luminosity to the brightness that we actually measure from Earth. This relationship is called Leavitt's law because it was discovered by the incredible and underrated astronomer Henrietta Leavitt, whose work in 1912 led to the discovery of this relationship, which then led to us being able to discover a Cepheid variable in our neighboring Andromeda galaxy and determine that it was in fact a galaxy and not a nebula. So thanks directly to Henrietta Leavitt's work, we can now measure the distance of galaxies up to 100 million light years away. That's way better than we can do with parallax. Okay, so the next type of standard candle can actually work at insanely far distances. This is called a type 1a supernova, and it's one of the brightest instances, one of the brightest things, phenomena, one of the brightest events in the entire universe. Now, this is essentially the result of an exploding white dwarf. A white dwarf is already kind of a dead star. It's like the skeleton that's left behind by a sort of low-mass star that has lived its life and turned into a planetary nebula. But oftentimes stars are in binaries, so what might happen is you might have a larger star that's paired with a white dwarf and they're orbiting around each other. As that larger star ages, it will begin to expand. And as it expands, it might fall into the gravitational well of the white dwarf. Now, what this means is that that white dwarf might start to accrete matter. This is problematic because a white dwarf can only sustain itself up to a certain mass. Any more massive than that and it will explode. This is called the Chandrasekhar limit, and it's around 1.4 times the mass of our sun. So if enough gas from that companion star falls into the white dwarf, it can overcome what's called the electron degeneracy pressure of that star and then explode. Now, this works as a standard candle because it will always explode at the Chandrasekhar limit, which means that it's sort of standardized amongst different examples of this. They always explode at 1.4 times the mass of the sun. When they always explode at that same mass, they will always explode with the same brightness, ergo we can use it to determine how far away it is. We'll recognize that's a type 1a supernova, and we'll compare how bright that recording we have of it is compared to the intrinsic brightness that we know of type 1a supernovae. Like I said, these are insanely bright, so we can actually use these to measure the distance of galaxies billions of light years away. Very, very, very far. So billions of light years away is good, but it's not good enough. We actually need something that can measure distances farther than that. For this, we have to rely on the intrinsic expansion of the universe itself. Spoiler alert, since the Big Bang, the universe has been expanding, and in fact, it's been expanding super, super quickly. From our perspective, when we measure distant galaxies, we can see that they're receding away from us at around 70 kilometers per second per megaparsec. That is to say that the further galaxies appear to be receding more quickly. Now, don't at me about that figure. 70 kilometers per second per megaparsec is about right, but actually it varies based off of who's measuring it and how they're measuring it. So yeah, don't worry about that. It's around 70 kilometers per second per megaparsec. So that constant is called Hubble's constant. And thanks to that constant, we can actually formulate a rather simple law called Hubble's law. This is V equals H naught D. Now we can actually reorient this to say D equals V divided by H naught. H naught is Hubble's constant, D is the distance, and V is the velocity at which a galaxy appears to be receding away from us. We know Hubble's constant, we can measure V, therefore we can find the distance to those receding galaxies. So we know H naught, but we don't necessarily know V. In order to find V, we actually have to measure how red a galaxy is. This is called cosmological redshift. As the universe is expanding, light actually gets stretched into longer and longer wavelengths. So blue light might turn into red light when it reaches Earth and hits our eyes and our telescopes. This is what happens when we're measuring very, very distant galaxies. Very distant galaxies appear literally redder because their light has been stretched over the course of the expansion of the universe. So we can actually figure out how fast something is moving away from us based on how redshifted it is. Oh, it's getting cold. So now we know the velocity of the receding galaxy and we know H naught, so we can determine the distance away from that distant galaxy. So that's pretty crazy. We have officially reached the end of the universe, the complete edge. That's as far as we can measure the distance to things, using the literal expansion of the universe itself and some fundamental principles of physics to determine how far away these distant galaxies are. It's pretty f***ing wild. So let's take a moment to look at all that we've accomplished. We've just climbed this massive ladder to the edge of the universe, where each step we took was calibrated by the previous step. It's pretty impressive that we've figured out how to look at cosmic distances like this. And all of this was contextualized by our journey through the history, right? We explored how we got to the point where now we've been able to put giant mirrors in space to collect light from the end of the universe. For all intents and purposes, our eyes and our minds are now at the edge of the universe. So take a moment. Think about what is it that we see exactly? What do you see at the edge of the universe? All I see at the edge of the universe is a mirror pointed back at us. Now, that's metaphorical, obviously, not literally. But think about it. We've come all the way from the ancient Babylonians as far as our astronomical discovery goes. That was 3,600 years ago. And think about all that we've accomplished in those 3,600 years. We've gone from the Babylonians to the Greeks to now the point where we can traverse billions of years of cosmic history with our eyes and our minds. We look out and we're able to explore and see and discover the universe. And eventually we've arrived at this point where we just were, the point where we've used fundamental physics and paired it with the expansion of the universe itself to measure how far away the most distant galaxies in the observable universe are from us here on Earth. Now, what does that even mean? When I stop to think about what it means to be measuring the stretching of light and corresponding that to how far away galaxies are, it just becomes helplessly abstract. Even though Earth is a part of the expanding cosmos, it feels somehow detached from it. It's almost like as astronomers, we've forgotten where we come from. We've forgotten where our bodies lie when our minds spend so much time out in the universe. We set out to explore the cosmos, but we've forgotten to explore ourselves. We've forgotten to actually take a moment and look at all there is around us, because the Earth is a part of the universe, as much as it might feel dissociated from it. This Earth is perhaps the most miraculous thing that we have discovered in our pursuits into space. So this is where I found myself towards the end of my studies of astrophysics. I had spent 4 years of my life with my eyes pointed up at the sky and my mind amongst the stars. And towards the end of it, I found myself yearning for this. I found myself yearning to learn more about the atmosphere that I live in, the Earth system that I'm a part of. So while I've spent 4 years studying the universe, I remember that my body rests here on Earth, as much as it might seem like my mind has been out there. And it might seem like the dissatisfaction of finishing that pursuit into astronomy is that I wish my body could join my mind in the stars. But in fact, it's the other way around. I wish that my mind would return to my body here on Earth. So it's the yearning to come back here to the Earth to study what it is that we are a part of. The Earth is a part of the universe, and we so seldom study it as astronomers. We forget to contextualize all that we are when we're studying the cosmos with what we are here. So the more you look out, the more you're forced to look in. This is that astronomer's paradox I was talking about. It's that battle between inner and outer space. So I found myself waking up towards the end of my undergraduate degree, which meant that I could no longer truly study astronomy. That is a win and a loss as far as I'm concerned, but it meant that I got to return back here to Earth. Now, this feeling obviously isn't shared with most astronomers. Most astronomers like spending their lives up in the stars. I don't know what forced me to start to look in and reflect. Perhaps it was that philosophy broke me beyond repair, because it's astronomy that contextualized the universe for me. Astronomy taught me to value and appreciate what we have here on Earth with its blue skies. I appreciate the blue skies not because of Rayleigh scattering, as we learn in astrophysics, but because it's a uniquely human experience to exist under a blue dome. Studies beyond our atmosphere paradoxically remind me to sit and breathe. Now we get to stop and look at the flowers and reflect on what makes Earth Earth, what makes it a uniquely special place to be. Our solar system has 8 planets, right? Only one of them has intelligent life. Only one of them has life at all, as far as we know. Now, if we think back to the cosmological distance ladder, as we left our galaxy using Cepheid variables and parallax, we passed a few 100 billion stars. Each one of these stars has a solar system with its own set of planets. So that means that we passed hundreds of billions, if not trillions, of planets on our walk up the cosmological distance ladder. Think about what that means for a moment. Think about how few of those resemble Earth at all. It's incredibly rare to have a planet that is habitable in theory, let alone a planet that's actually inhabited. Now, within this galaxy of ours, we've actually formally studied almost 6,000 exoplanets. It's like 5,800 or something like that. We haven't been able to prove that a single one is like Earth at all. We haven't been able to find life. Life just woke up on this curious and beautiful planet of ours, and that is something incredibly special. So I obviously value the study of outer space and outer space itself. The universe is a remarkable and beautiful and strange place. But I think that part of what gives the universe that beauty is the beauty of Earth, and vice versa. They give each other that meaning. The universe wouldn't be as strange and peculiar and beautiful as it is without what we perceive as normal to be Earth. And to those who are familiar with astrophysics and studying outer space, if you can just shift your perspective a little bit, Earth will become all the more beautiful when you remember the context of everything. This, once again, is the astronomer's paradox, the battle between the Earth being distinct from the universe and the Earth being a part of the collective universe as a whole. Our minds may be in the cosmos, but our bodies rest on this marble of green and blue. Yeah, look at those crows.